is being returned back to you. There are 3 stacked here. They are alphabetically arranged. Okay, so please pass on down. If it's not in the stack, do you know what alphabetical?
It's like A through H and then
A
H through like
A
G.
through H, just so that you know which is which. Which will be this step. They're not alphabetical arranged, but that's fine. I think you can sort it out. The other 2 stack are what? Letter.
I don't know if it's exact, but it might be like H through P. Or I.
So you may have to sort through them all. It's not quite arranged alphabetically, but hopefully that won't take you too long. So the average is 70, much lower than the first test. As such, there are several problems in the test I'd like to go over. So what I want to do today, this is part of the agenda, is to go over the first 2 problems, 1 and 2. That's especially number 1 is the problem that is most difficulty with. And I will state the problem again in the lecture so you can rework the problem as a homework. Right here, problem 1 and 2. I think that will be very beneficial for you. If you have done it correctly, you don't have to do anything. Otherwise, I think it will be a good exercise for you to go over both problems. And the next lecture on Thursday, we go over problem 2 and 3. And then I'd like you to rework that too. Yes?
So that'll be like part of the homework, or?
That's part of the homework, yes. That's part of the homework, correct, yes?
So if we did it correctly, should we take a picture of our test?
If you do it correctly, yeah, just take a picture of your test and don't have to do anything, correct? Right, yeah, so if you've done both one correctly, there's nothing for you to do. Otherwise, you may want to rework it just because they're good problems for you to reinforce the basic and the fundamental. So that is being passed around. And today I just want to touch on the drag coefficient because the next set of homework also uses that. And we hastily talked about separation last time. I want to go back and just reinforce some of the important concepts. And with that, we can look at why the dimple on a golf ball. So we're going to study in some detail the flow around a spear, basketball, baseball, golf ball, etc. And then we will also start a new chapter, going way back to chapter 4. So the reading assignment is going backward, chapter 4, to look at something called a flow field. What does that mean? What is meant by a flow field? And that set the stage for a new nomenclature, a new set of vocabulary. So the reading is continuum boundary layer, separation, drag coefficient, etc. And then going back to look at velocity and acceleration field. What does that mean? And that will set the stage for future homework. The homework due on Thursday is on the lighter side, 2 hours, depending on how much work you have to do on the rework of the test problem. Then 2 new problems, 14 and 15, is just very simple plug and chop that use this set of equations. Right? So there was some question about the use of those equations. I just want to touch on it in reference to the homework due today. Maybe just a repeat that most of you have a good grip of. So problem for the homework due today asks you if I have a laminar boundary layer and the velocity in the free stream change from u, which is the baseline, to twice the value or half the value, how much that will influence the drag. How would they compare when you change the free stream velocity? Everything remains the same, viscosity and so forth. So all that boils down to is the use of this equation here, which is what I call integrated friction drag. So the numerator here is the drag force. Integrated, meaning all from the leading edge onto a specific distance of length L from the leading edge. That, in most cases, is all you care about. An overall effect due to shear that worked itself as a friction and created what we call the friction drag, the shear drag, different from the pressure or form drag. And those nomenclature, do you have any question how to use this? This is nothing new, I'm just clarifying some of these concepts that some of you may have. So what happened here when you change the velocity is you're changing the Reynolds number. All right, and the plug-in charge is straightforward and very simple. And the next set of homework, very similar, laminar boundary layer. That's all we have, an analysis and the formulae that we can use. Turbulent is a little different, we'll cover that later. And it's different from this local drag coefficient. Do you see the difference? Do I have to explain that again? Can you see these two formulae, distinguish the one from the other? If you have a question, I'll be happy to answer it. If not, I will just move on. And do you know the significance of this X in here? And do you know the word local? What does that mean? Any question, please? Now is the time to open that for discussion. Yes?
That just means it changes as we go down the.
Absolutely. So the local meaning at a point. So not using the same diagram, but the local meaning I am from the leading edge at a specific point of distance x from the leading edge at that very point, and that single point only, locally at that very point. What is the drag coefficient? Okay? Whereas the second equation is a average integrated overall frictional force due to each of those small pieces. Yes?
And that's only if the entire boundary layer flow is laminar?
Always. Very important. Laminar flow. That is the only way where we can nicely solve that equation of viscous flow. Turbulent is far more complicated. And all the turbulent analysis by and large are experimentally based. It is true, laminar and incompressible. So very restrictive, but give you just a little bit of taste of how one can deal with friction due to shear, due to viscosity, purely, but no contribution, at least for a simple plate of pressure drag or so-called form drag. Is that clear? There was another hand over there. Other questions? Okay, so we have put that aside. So far, all those are just formulae you can use in about 2 or so lecture. We will hope to prove to you by solving this equation of boundary layer, viscous flow, how the equation come about. And that takes a lot of in-depth thinking that we can at times completely confuse. And even prior to that, I have to establish all that differential nomenclature, the acceleration field, velocity field, and that's the subject of chapter 4. All right? So we're progressively doing a deep dive into differential analysis. Other questions before I touch on this concept of separation? So for separation, the takeaway, the things I want you to remember the most is this so-called different pressure gradient. The equation on the right, and I almost missed that detail, in addition for laminar boundary layer, had another very severe constraint. There's no pressure gradient imposed on this boundary layer on the plate. So as I march downstream, the pressure is always constant, called 14.7. No change. However, for most entry devices, and also a diffuser, a compressor, and a turbine, that's far from being the case. They have, on average, between the downstream station and the upstream station, significant pressure gradient. So I have the first case, dpdx, being increasing, positive. The other case is decreasing. For the decreasing case, where I go in the direction of X towards that door, each step I march, the pressure actually is smaller. We have a very important name that will go with that. What kind of pressure gradient we call that? If you look back at your note last time. And the opposite of that is where the pressure is actually increasing as I march towards the door. We use two particularly just to remind us to raise the red flag. So in the second case, where the pressure is dropping, like in the turbine, what do we call that pressure gradient? Favorable, very good. That's what I want you to remember. And it's very important. It just seems so trivial. It's the next one that I want you to make sure you never forget. What do we call that pressure gradient? Adverse. When you hear the word adverse, does it mean good or bad? Bad. Bad. And it is. Anytime you have a device where the pressure is increasing downstream, compressor, a diffuser, it's called adverse pressure gradient. And this is where I want you to raise the red flag and be on alert, because it will cause the boundary to do what? Separate. Separate, for the reason we discussed last time. The low momentum tire, literally like coming to class Monday morning. Very tire fluid near the wall where the momentum is already small. You subject that to a force that is opposite the direction of where you're going, I'm going to give up. I'm not going to march towards the door anymore. I'm going to let the force, due to pressure, push me back. And that separation is caused what an airplane to plummet or losing lift, because the boundary layer just peel off completely on the suction side or the upper side of that airfoil, and all hell break loose. This is bad for a lot of phenomena, like an airplane stall, an aircraft engine stall, fall completely break down in the diffuser saying boundary layer separated, all of a sudden the blockage become much more, and the intent of the design of that engine device